Hello.
O- Okay, hello. Okay. So I am going to talk on semiconductor
Hello.
device modeling. Hello, hello, hello. Okay. So I am going to
Hello.
talk on semiconductor device modeling and simulation. So nowadays, modeling and simulation is the very important area in the research and industry. Most of us are aware about models. So for example, some builder or architect wants to construct a building. So he first prepares a model, small model of the building, means how that building will look and how windows and doors and structure of building will look. So there is lot of issue is there. Hello, lot of echo is there. Okay. Okay. So we are aware about the models, but see that is not simply a model of building. There are several different types of models in science and technology. So the model of building is simply one of the examples of the models, that is physical model. But there are several types of model: analog model, digital model, static model, dynamic model, statistical models like that, probabilistic models. So mathematical models, analytical models. So if you look according to science and technology, so to model particular device, process or system, what is needed is the mathematical equation. So we are interested in mathematical modeling and its simulation. So next slide, madam. Modeling and simulation are very closely coupled, closely related areas in science and technology. And these two areas help the scientists to reduce the cost and time consumption for the research. Even ordinary people who don't understand how the machine will be operated, that can be simulated and training can be given to such ordinary people. Next, madam. So what is modeling now? Modeling is a creating a model means which represents object or system with its all or subset of properties. Means model may be exactly similar as that of original system, or some approximations have been made, but it is simply imitation of real entity. And mathematical model needed for scientific research describes system of equations. And as I have told you, modeling can reduce cost of process and make the process faster. Next slide. Now, what is simulation? Simulation is technique of studying and analyzing behavior of real world or an imaginary system by mimicking it on a computer application. Means instead of actually developing that device, instead of fabricating actual device, you can predict the characteristics of that device in advance by simulating that device using mathematical equations. So what it needs is a mathematical equation of that particular device, process or system. So in simulation, you can simulate, predict the behavior of that system or device by changing one of the input parameter or variable and track the changes in the output. Means if I will give such kind of input, what kind of output I will get, that you can predict in advance. without fabricating actual system, device, or process. Next. Now, modeling versus simulation. Both computer modeling and simulation are recent applications. And as I have told you, it saves a lot of time in the development of product and money. Because if you see, try to fabricate the product on trial and error basis, it consumes a lot of time. And simply, it causes number of cycles to repeat and material wastage. And so it's not economical approach. So to save the money and time, modeling simulation is the proper approach. So in simulation, what we are doing, as I have told you, one of the input parameter you can change. If this is the input, what kind of output I can get, that you can track. So model always tries to represent actual system, while simulation try to observe the result, predict the result by doing impossible changes. Means, for example, if you want to see, say predict temperature at the core of sun, is it possible to go at the core of sun and they measure the temperature? No, it's impossible. You cannot reach up to the sun to measure the temperature. But using modeling and simulation, you can predict, you can see, uh, do simulation and
Tiraj.
calculate the temperature at the core of sun. So in this way, impossible things can be simulated. Model can be considered as a static, but simulation can be considered as a dynamic, because in simulation, you can observe the changes in output as per the change in input. And that's why simulation is a dynamic phenomenon. Next. Now, semiconductor device models. So, semiconductor device models are classified into two groups: equivalent circuit model and physical device model. Equivalent circuit models are based on electrical performance of the device, and we try to represent diode or transistor in the form of passive components and predict the performance of the device. So equivalent circuit model can be a approximation. It is approximated, and it is that's why it's not suitable for predicting performance of new device structures, novel device structures. But devices which are existing, you can prepare equivalent circuit model for those devices. And equivalent circuit models are quite simpler in comparison with physical device models, because physical device model takes into consideration actual process needed for fabrication of that device. And so device physics comes into picture, and so many physical and mathematical equations are to be considered for physical device model. So for example, physical device model may take into consideration carrier concentration, thickness of particular layer, then how much bias voltage is applied to that device, what is the range of voltage, like that. So physical device model is a complex phenomenon, and it's complex in comparison with equivalent circuit models. Next. So equivalent circuit models, say this is simple example of NPN transistor represented in the form of coupled diode model. Say NPN and PNP is considered as a back-to-back connection of two diodes. And this is on right hand side, it's a last signal model which is showing the equivalence of transistor. Next. Now semiconductor device model. Carrier transport in semiconductor devices can be classified based on three types of models: classical model, semi-classical model, and quantum models. Classical models, of course, are based on classical approach and using Boltzmann equations. Semi-classical model. Semi-classical model uses both approaches, classical and partly quantum. That's why they are called as semi-classical. And so semi-classical models involves some classical equations and some of the quantum equations. For example, for scattering effects, quantum equations are needed, and for calculating simple means motion equation, motion of carriers, classical equations are used. So in semi-classical, mobility and diffusion coefficient are considered as function of instantaneous electric field. Now quantum models are purely based on quantum mechanical equations. So always quantum models begins with Schrodinger equation. Next. Now technology trend. So we know with the development of technology, electronics technology, so development begins in 1900 here with vacuum tubes, which are approximately of size 10 centimeter. So with the development of transistor around 1950, major breakthrough took place in the electronics technology because size of transistor is too less in comparison with size of vacuum tube. So size of transistor is in say 1 to 2 centimeter only. In 1960, scientist Kilby has proposed the concept of integrated circuit, and size has been further reduced to millimeters, and he was awarded with a Nobel Prize for his efforts. In 1970, concept of large-scale integration, SKM, and more components are fabricated within integrated circuit chips, and size is further reduced to 10 micron. And in 2000, concept of ultra large scale integration has came, and size is reduced to 100 nanometers, and now Intel is trying to reduce a feature size up to 7 nanometer. 22 nanometer is a trend now in the market, but Intel is further trying to reduce this feature size to 7 nanometers. So in 100 years, size of components has been reduced by 1 million times. Tremendous reduction of size we are observing in the human history, and which leads to very complicated device development and chip development process. Next. Transistor scaling, as we know, day by day feature size has been reduced, and as feature size has been reduced, speed of the device has been increased, because it's so simple. As feature size is reduced, gate length is reduced. As gate length is reduced, less time is taken by electrons to travel from source to drain in MOSFET, and so speed has been enhanced. Again, size is proportional to power. As size has been reduced, device needs very low power and it dissipates very low power. Then as speed has been increased, high frequency operations are possible with the devices. And of course, with the scaling down, space has been reduced, area of the chip has been reduced, but at the same time, complexity has been increased because we are trying to accommodate more and more components in the small size of integrated circuit. And so density has been increased. It becomes dense and dense. Next. Now, modeling nano devices and parallel computing. So as I have told you, as feature size has been reduced to a nanometer scale, device behavior becomes the complicated. Classical models are no more applicable to nanometer size devices. So always quantum mechanical models are used, and so complexity of modeling and simulation has been increased, and so more and more efforts are needed to understand nano size effects and properly compute such a physical quantum mechanical equations and to arrive at an accurate solution of the at the end of simulation. Next. Now, what is computational electronics? So computational electronics refers to physical simulation of semiconductor devices. Of course, in terms of charge transport and corresponding electrical behavior. Means what we are simulating? We are simulating how electrons are flowing through device, how holes are flowing through the device. That is called charge transport. And corresponding electrical behavior relates to a flow of current once bias is applied to the device. So depending on customer need, what kind of the device customer wants, process simulation is carried out, device simulation is carried out, then parameters are extracted, circuit level simulation is carried out. If simulation is optimized, no, again go back to process simulation. Once it is optimized, you can arrive to conclusion. Next. Now, basic elements of device simulation. So, what device simulation exactly needs? Transport equations. Transport equations means drift diffusion equations, current density equations, carrier transport equations, along with electromagnetic fields. If device is light emitting device, electromagnetic field plays an important role because light is electromagnetic wave. Next. Now, hierarchy of transport models. First one is compact model, then drift diffusion equation, hydrodynamic equation, Boltzmann transport equation, quantum hydrodynamics, quantum Monte Carlo method, quantum kinetic equation, Green's function method, direct solution of n-body Schrodinger equation. So first four are the semi-classical equations. And if you consider first only, first and second may be considered as a classical models. But if you consider mobility and diffusion coefficient as a function of instantaneous electric field, then drift diffusion equation comes under semi-classical model. Then remaining 5 to 9 are pure quantum mechanical models, which are used for nano-sized devices. Next. Now nanoscale transistors. So here say as size, if you compare the size, see if size of device is 10 micrometer, then you can use classical transport equation. If size is less than 200 nanometer and greater than 100 nanometer, then it leads to velocity overshoot, and so one-dimensional quantum effects need to be considered. If size of device is in between 20 nanometer to 100 nanometer, we have to consider quantum effects as well as dopant fluctuations. And if size of device is less than 20 nanometer, then we will have to consider purely quantum mechanical equations, all the quantum effects and ballistic transport equations. Next. So what are advantages and disadvantages of existing semi-classical simulators? So as I have told you, if gate length is greater than 0.5 micrometer, then you can use drip diffusion model for the simulation. But if there are hot carrier effects will not be considered using drip diffusion model. If gate length is greater than or equal to 0.1 micron, then hot carrier effect such as velocity overshoot is included. And if gate length is less than 0.1 micrometer, then particle-based device simulation need to be considered using quantum mechanical equations. And that is very time consuming, needs more effort, and needs a proper understanding. Next, which model is to be used now? Now, different transport models are existing. Now, depending on your application, device dimensions, geometry, you can use a proper transport model. Now, if device dimensions are in nanometer, then you will have to consider quantum mechanical models, as I have told you. And if device dimensions are in micrometer, then you can use classical or semi-classical models. Next. Now, semiconductor device modeling creates a models for behavior of electronic devices based on fundamental physics, such as doping profile of device, as I have told you. And for IC fabrication, we'll have to consider electrical and mechanical characteristics. And for process simulation, you will have to consider so many process parameters while fabrication, like temperature, pressure, flow rate, dopant concentration, like that. Next. Now, why semiconductor modeling? Semiconductor modeling is based on computational mechanism and writing, say, simulation program, optimizing the design of the device, and avoiding a costly and time-consuming trial fabrication. So SPICE is a simple example of simulation program. Simulation program with integrated circuit emphasis transistor models. It is quite popular to predict behavior of transistor characteristics. Next. Now, why quantum nanostructures? So nowadays, we are talking about nanotechnology. And with the development of nanotechnology, we'll have to consider nano-sized dimensions of the devices and quantum mechanical effects in those devices. So devices based on quantum mechanical models are called quantum nanostructures. Actually, nano size particles were existing in nature since the creation of Earth. Till everybody is now talking about nanotechnology. Why not earlier people were talking about nanoparticles? We don't have vision at that time to visualize nanometer size particles, although they were existing in the nature. But with the invention of scanning tunneling microscope, it became possible to visualize nanometer size. And then we came to know that, yes, nanometer size particles are existing in the nature and their behavior is different as that of bulk particles. So for light emitting devices, quantum nanostructure plays important role. They provide high radiation efficiency due to quantized states, due to small volume and high carrier concentration. And quantum nanostructures if used for light emitting devices, they provide a low threshold current and lower carrier density for population inversion. So in bulk material, if you compare bulk with quantum, nano, in bulk material, electrons and holes can move freely along 3 dimensions, x, y, or z direction. In quantum well, electrons and holes can move freely only in 2 dimensions, and their flow is restricted along one axis. In quantum wire, electron can only freely move in only one direction, and its flow is restricted among 2 directions. And in quantum dot, flow of electrons and holes is restricted in all 3 directions. Means electrons and holes are not allowed to freely move among 3 directions. They are confined. And as they are confined, it's very easy to achieve population because they remain stored at a particular volume in the device. Next. So what are nanostructure applications? Nowadays, nanofets are available. Thermoelectric efficient materials are constructed from nanomaterials, light emitting diodes, detectors, sensors, nano lasers, then nano interconnects in very large scale integration technology. Next. So development of nanotechnology is based on 3 basic things. So as I have told you, fundamental understanding is necessary to understand any nano-sized device. Then modeling and simulation is needed to properly understand behavior of this nano-sized device. And once simulation results are available with you, you can go for experimentation and characterize that device to predict desired characteristics. So modeling and simulation plays a very important role in the innovative research and new technology. Next. The actual history of nanotechnology began in 1959. Feynman, one of the great physicists, in one of the conferences said that there is a plenty of room at the bottom. So he has to say that on a tip of needle, information of whole world can be stored. Means you can fabricate such a miniature device which can store lot of information. So this statement was made by Feynman in 1959 itself. There is plenty of room at the bottom, and his statement become evident nowadays with the development of nanotechnology. Next. So discovery of scanning tunneling microscopy leads to vision of nanotechnology. So with the development of scanning tunneling microscopy, it became possible to visualize atoms and molecules having nano dimensions. So credit goes to Binning and Roller, and they were awarded with a Nobel Prize in Physics in 1986 for development of scanning tunneling microscopy, due to which we can able to identify, we can visualize nano-size objects. Next. Now, why simulation is needed? So as I have told you, it reduces fabrication cost. because number of trials are reduced. Once you come to conclusion that, okay, you have to take this much thickness, this much carrier concentration of the device, this is the flow rate, this is the temperature, like that, like that. That is the dopant concentration, proportion, like that. And so you come to with a optimized set of parameters, which you can use for your experiments. And so development cost, fabrication cost is reduced. Again, as I have told you, simulation gives results that are not experimentally measurable, just like temperature at the core of sun, as I have told you. Then to analyze behavior and performance of complex nanostructure, simulation is very, very useful. So working with simulation starts with developing the model for nanostructure, then define material and physical parameters, search appropriate computational techniques, implement the model through computer simulation, then predict output characteristics and optimize finally the result. So this is flow of the simulation. Next. Now, again, one of the great physicists who proposed the electric and magnetic field equations. All these equations are needed for the device simulation. So Maxwell demonstrated electric and magnetic field traveling through space in the form of waves. And he tried to correlate electric equations with a magnetic equation, or try to correlate electric field with a magnetic field through his equation. Next. So these are the derivative form of Maxwell's equation. Del cross E is equal to minus del by B by del by T. Del cross H is equal to J plus del by D by del by T. Del dot D is equal to rho. Del dot B is equal to 0. These are the equations, Maxwell's equation. Next. Now, if you have to simulate nano size devices, very small size devices, Schrodinger equation is always needed. So Schrodinger was awarded with Nobel Prize in 1933 due to the wave equation he has proposed, which gives probability of event or outcome. Next. Now Poisson's equation. This is again one of the very fundamental equation in physics derived from Maxwell's equation and needed for device simulation. So considering Maxwell's equation, del dot D is equal to rho, where D is electric field displacement, rho is charge density, but D is equal to epsilon E, as we know. Substituting value of D, it becomes del dot epsilon E is equal to rho, but E is negative gradient of electrostatic potential. And so again, if I substitute that value of E, then equation becomes del dot epsilon del psi is equal to minus rho. This is Poisson's equation for heterogeneous media. If you consider epsilon constant, then epsilon is taken outside derivative and taken to right hand side. And so equation becomes del square psi is equal to minus rho upon epsilon for homogeneous media. Now heterogeneous and homogeneous media means what? In heterogeneous media, value of refractive index is changing from layer to layer, or in heterostructures where there are more than one materials are used. Of course, refractive index of one material is different as that of different material, and so heterostructure uses this equation del dot epsilon del psi is equal to minus rho, because epsilon is changing from layer to layer. While in homostructures, where epsilon is constant throughout the material, you can use this Poisson's equation. Next. So now Poisson's equation, how it is used for simulation. So finite difference discretization can be used to determine potential profile in the device. So in finite difference technique, what you can do, you can divide your device into number of mesh points. Now, depending on number of mesh points, you will get accurate results. If you select less number of mesh points, accuracy will be less. If you select more number of mesh points, you will get more accuracy of electric potential or potential profile. The next. The finite difference method, say, deals with dividing your device structure in the form of mesh, and at the intersection of vertical and horizontal line, we will get a node that is called nodes. Now, at these nodes, you will have to solve the Poisson's equation to determine the potential. So what you can do, if it's one dimension device, you can use one dimension Poisson's equation. It's, for example, del square psi is equal to minus rho upon epsilon. So you can take delta 2 psi by delta x square is equal to minus rho upon epsilon in 1D devices. In 2D devices, you can consider two dimensions along x and along y. So you can discretize the derivative amongst two dimensions, like delta 2 psi by delta x square plus delta 2 psi by delta y square. In this way, del square is considered in two dimensions. And you can solve the Poisson's equation at all these nodes, and you will have to converge the potential till you will arrive to a proper accuracy. Next, so what is considered for finite difference method? Taylor's series, which we have studied in class 12. F of x plus h is equal to f of x plus h f dash x plus s square by 2 factorial f double dash x, like that, where h is very small. So higher order terms can be neglected. So f of x plus h is equal to f of x plus h f dash x. And so f dash x can be calculated from this formula, that is f of x plus h minus f of x upon h. So this is forward difference formula if you have studied numerical technique. Then higher order derivatives like second order can be discretized using again Taylor's series in the similar manner, and f dash x is equal to f of x plus h minus 2 f of x plus f of x minus h upon h square. In this way, higher order derivatives can be discretized using Taylor's series. Next. So now simple classical approach uses drift diffusion equations. So drift diffusion equation involves Poisson's equation. So Poisson's equation is used to determine potential profile of the device. And again, as I have told you, del dot epsilon del psi or del V electrostatic potential is equal to minus rho. Minus rho is P minus N plus Nd plus minus Na minus, that is charge density. Continuity equations are considered. So where delta N by delta T represents electron transport in the conduction band, and delta P by delta T provides a hole transport in the valence band. Then current density equations are considered. Current density equations are again based on drift diffusion approach and involves mobility, diffusion coefficient, and electric field. Next. Now, carrier transport equations involves a generation and recombination mechanism. That term is there, R term is there, G and R. G is generation rate, R is recombination rate. So in thermal equilibrium, balance exists between generation and recombination of electrons and holes. But this balance may get disturbed due to several physical mechanisms like thermal recombination due to phonon transitions, impact ionization in the semiconductor, Auger recombination, surface recombination, optical generation and recombination. And so total generation and recombination rate is sum of all these processes or all these parameters. Next. So now thermal. Thermal is attributed to phonon transition occurring as a result of traps. So in semiconductor, there exists a defects, and when electron takes a transit from valence band to conduction band, maybe this trap will absorb that electron. So this kind of, say, recombination is proposed by Shockley, Reed and Hall, three different scientists. And so sometimes this recombination is referred as Shockley-Reed Hall recombination. Name of scientist has been given. So again, it involves an indirect process in the energy band gap, and it is non-radiative recombination. Means when electron takes a transit from valence band to conduction band, we expect that electron should again fall back to valence band and emit a light in direct band gap semiconductor. But what happens in indirect band gap semiconductor or defective semiconductor, trap exists in the band gap, and electron may not fall properly to the valence band and may get absorbed, and so it will not lead to photon emission. So energy that is released due to transition of electron is converted in the form of phonon, lattice vibrations. Now next type is impact ionization recombination. So as the name suggests, it involves the impact. When electron and hole pairs are generated in semiconductor, they attacked on the, again, third particle, again different electron and hole. And so again, energy is not liberated in the form of photon, but it is delivering that energy to different electron and hole. And so again, it is non-radiative recombination. The next form of recombination is Auger recombination. It is considered reverse as that of impact ionization. So here, electron and hole pair, and see what it emits in direct band gap semiconductor is again, see, delivering energy to third particle, but energy is absorbed in the trap. It is again not radiative. Next is surface recombination. So as we know, semiconductor surface is a source of dangling bonds. Lot of dangling bonds are present. As we know, silicon is a tetravalent atom surrounded by 4 atoms. What about surface? Atoms which are present on the surface. On the atoms which are present on the surface, they are not covered with a covalent bond because air is present on the surface, and so that is considered as a dangling bond. And so surface of semiconductor is again source of impurity. Lot of dust may sit on the surface of semiconductor, and so such kind of recombination is considered as a non-radiative. The next is optical generation and recombination. So it involves spontaneous and stimulated recombination. Now, optical generation and recombination, they are additive recombinations because they are going to generate a photon in direct band gap semiconductor. And so they are additive. So spontaneous emission occurs naturally. And so in light emitting diode, we observe spontaneous recombination. But for laser, we need a stimulated emission for coherence. So spontaneous and stimulated are related with light emitting devices and they release the photon. Next. Now, what is the approach that is used for discretization, finite difference discretization? Electron and hole densities vary exponentially in transport equation between mesh points. And so it needs different computational efforts. So I did my research in the computer simulation and I wasted near about 6 months while solving this transport equation. Wasted in the sense I studied a lot, I learned a lot during that period because I was not arriving at a proper conclusion. I was considering N and P varying linearly between mesh points because I was not getting a reference during those days. I was trying to simulate transport equations similar as that of Poisson's equation. And that's why I am not arriving to a proper conclusion. But referring so many books, studying mathematics, studying physics, lot of physics, studying solid state physics, Stittmer's book, then Kittel's book, solid state devices, optoelectronics book, and research papers. Then I came to know that transport equations cannot be solved linearly. It needs different computational approach. And I have changed my approach and I got the solution within 6 months. Next. Numerical solution details of coupled equation sets. See, what kind of approach should be used? Gumel's approach. Gumel's approach optimizes individual equation, converges individual equation, and so equations are weakly coupled. Newton's method uses strong coupling between transport equations and Poisson's equation. But if you combine the approach, Gumel-Newton mixed approach, it provides a better computational efficiency. Next. So it shows the original Gumel approach. In original Gumel approach, what he did, Poisson's equation is solved individually. It is converged first. And then transport equations, electrical equations has been solved for electron and hole. And they are again converged separately. But this is not efficient approach. So modified Gumel scheme is used. In modified Gumel scheme, what is done? Poisson's equation is solved at a particular node. Then transport equation for electron and holes are solved. All three equations are converged at the proper node. If they are not converged, again go back till they will get converged. In this way, self-consistent approach has been used here. All three equations are solved in self-consistent manner. Once electrical equations has been converged, then you can go for generation rate, optical equations, and then optical equations has been converged. So modified Gumel scheme provides an efficient approach for the simulation. Next. Now when deep diffusion model is valid, so as I have told you, it is a classical model used for large devices, bulk devices. where velocity of carriers is smaller than the saturation velocity. Then you can use classical model. But when velocity will get saturated, we will have to consider dependence of diffusion coefficient and mobility, electron mobility on instantaneous electric field. And so it becomes a semi-classical approach. Next. Now, how two-dimensional equations are solved in finite difference method. Suppose we will have to compute potential at ij node using a Poisson's equation. Then one must know potential around neighboring nodes. I minus 1j is left node, I plus 1j is a right node, ij plus 1 is up node, and ij minus 1 is a down node. If you know potential at all these 4 points, you can determine approximate potential at ij node in first cycle itself using this standard difference 5-point formula. Now next, now how this mesh is generated. So if your device dimensions are uniform, means thickness of each layer is same, you can keep same distance between two different nodes. Means you can create a uniform mesh. This is called uniform mesh because distance between any two adjacent nodes is same. So if you use uniform mesh, computational efforts will get reduced. Easily, you can apply your logic to write a simulation program and converse the equation. Next, now non-uniform mesh. Non-uniform mesh, see here, distance between two neighboring nodes is not same. It is varying. So it needs different computational approach. More computational efforts are needed. And most of the electronic devices uses a non-uniform mesh approach. Why? Because device dimensions use different layers of different size. Not all the layers are of 1 micron size. See, some of the layers are of 0.5 micron, some of the layer is of 0.1 micron, some of the layers are of 10 micron, like that. And so we need non-uniform mesh. And so computational efforts will increase, simulation complexity has been increased for say solving potential or electron transport, hole transport at all these nodes in non-uniform mesh. Next. Now for nano dimensions quantum mechanical devices, always your simulation begins with Schrodinger equation. So one has to solve Schrodinger equation with electric field and assuming phi is equal to 0. Then obtain general solution of Schrodinger equation, determine arbitrary constants, solve transcendental equation to determine eigenenergy, and obtain wave function distribution. Because Schrodinger equation leads to wave function distribution of the particle. Next. So semiconductor light sources. If you are simulating for light emitting devices, so again complexity has been increased because along with electrical equation, one has to solve the optical equation. So generally direct bandgap semiconductors are used for emission of light, and indirect bandgap semiconductor are not preferred for light emitting devices because photon is not radiated from indirect bandgap semiconductor. Energy is absorbed in the form of phonons, lattice vibrations, creates a heat. And so direct bandgap semiconductors are used for light emitting devices. Next. For light emission, nowadays, for short wavelength devices, zinc oxide and gallium nitride, these are the popular materials which are used for ultraviolet and blue light emitting devices. Next. So what are lasing conditions? For laser, again, laser involves a spontaneous emission. Population inversion is the necessary condition. Oscillation condition need to be satisfied for laser. And so simulating laser is quite complicated. So for laser, what is needed? Carrier confinement. Electrons and holes should be properly confined to achieve population inversion. Then optical confinement. Light should be confined properly to achieve a gain and stimulated emission is possible. Then only photon is emitted. And what is needed? Defect-free semiconductor. Because if there are defects in the semiconductor which you are using for laser, most of your carriers will get absorbed in the traps or defects. And so they will not lead to emission of photon. And so simply energy is lost in the form of heat in the crystal lattice. So how semiconductor laser should be? It should be small in size. It should be fast in operation, low cost, small power consumption, and it should provide a longer life. Because nowadays, the people are working with short wavelength lasers. They are not lasting longer. Their life is limited. And so lot of research efforts are needed to enhance the life of such a short wavelength lasers. But long wavelength lasers provide a better life. And it is now mature technology. IR lasers are available, which are used in optic fiber communication technology. Next. Now, self-consistently, how electrical equation has been solved for nano devices. So as I have told you, your simulation begins with Schrodinger equation, then calculate Eigen energy, wave function, quasi-Fermi potential, calculate electron density, hole density, solve Poisson's equation for potential profile, and then again solve Schrodinger equation with a new phi modified potential. If these equations are converged, then go for optical equation. If not converged, again go back till equations will get converged with a proper accuracy. Next. Now, why quantum well lasers? Why quantum nanostructures? Quantum nanostructure provides low threshold current due to quantization of energy levels and provides a better efficiency than bulk heterostructure. Next. So this is a gallium nitride based quantum well device which we have simulated in our laboratory, and simulation has been done through MATLAB software, and all these equations has been solved. Schrodinger equation, Poisson's equation, carrier transport equation, wave equation, photon density equation, and we lead to such a simulated results in our laboratory. Next. Now see, this slide shows probability density for varying quantum well width. And right hand side shows as we change aluminum mole fraction of the barrier layer, how means probability density profile is changing. Next. So this shows the electron density profile by solving electron density or carrier transport equation for electrons. And again, it has been solved through MATLAB in our laboratory. Next. Next slide shows the optical gain, which is necessary for laser. So it shows optical gain for different carrier concentration and with varying aluminum mole fraction. So as mole fraction, aluminum mole fraction is a greater, naturally it provides a better confinement of carriers. Carrier concentration is betterly confined to active region, and we will get a greater gain. Next slide shows a confinement factor. So as I have told you, as we increase aluminum mole fraction, confinement of carriers will go on increasing. And right figure shows change in the confinement of the probability density function with varying aluminum mole fraction. Next. Then we have simulated superlattice and multiple quantum well structure. And we got again result of probability density with varying aluminum mole fraction like this. Next. Now this slide shows peak optical gain at 375 nanometer wavelength for zinc oxide, magnesium zinc oxide quantum well. And again, we are getting optical gain for varying the photon energy. Next. Next, we have simulated a quantum nanowire. And again, it shows the confinement of probability density at the center of active region. Next. Next slide shows near field intensity in a aluminum gallium nitride zinc oxide composite structure. Next. Again, this slide shows confinement of mode 0 and mode 1 in the nanostructure. Next slide shows near field in the single quantum well for the varying dimensions. Next, this shows electron concentration distribution, again for varying the bias voltage. Next slide shows again this varying aluminum mole fraction, how polarization will get affected. Next slide shows optical gain. Optical gain as a function of aluminum mole fraction with varying carrier concentration. Again, for large carrier concentration, we will get better gain and better results. Next. Again, this slide shows simulation of nanowire structure for varying dimensions of nanowire. Now next slide shows simulation of square dimension nanowire. See how field is confined. Next. Then we have simulated a quantum dot in our laboratory, and we got very good results for zinc oxide 𝐬𝐲 nanodot. Zinc oxide quantum dot is confined within 𝐬𝐲 from all the sides. And we did the simulation of this. Next slide. So this shows a zinc oxide quantum dot confined within 𝐬𝐲 barrier layers. So 𝐬𝐲 naturally provides a confinement to zinc oxide quantum dot because 𝐬𝐲 is having less refractive index in comparison with zinc oxide and is having greater energy than that of zinc oxide. So it provides natural electrical and optical confinement for the quantum dot. Next. So these are the results of confinement which we have obtained for quantum dot. And the right hand side figure shows how the field is confined within the quantum dot. Exactly. Next. Thank you very much for your patience. And I would like to thank principal, management of Pratap College Amalner and organizers for giving me opportunity for this talk. Thank you very much. If you have any questions, you can ask.
Yes, I request participants if they have any questions. Please raise your hand. Participants can unmute themselves and ask the question. Yes, Mansi.
Really, thank you so much, sir. We are really honored to have such a great and studious speaker between us. We got a huge source of knowledge and advances in device simulation, which will be really very fruitful to study further in electronics. We are grateful about that. Hats off to your knowledge. Again, thanks to you and thanks to all of you also, because from 12 p.m. you all are with us. That's why we need to take a break till 2:30 p.m. We assure to each other that we will join this webinar after some while, sharp on 2:30 to hear again such great kind of guidance. Okay, guys, we will catch at 2:30 p.m. Thank you so much.
Yes, sir. अ, हां, मग 2:30ला स्टार्ट कराल सर. परत? ओके.